In Chemical Equilibrium 2, I'm going to teach you about Le Chatelier's principle, named after the scientist Henry Louis Le Chatelier, whose principle states that an equilibrium system subjected to a perturbation will shift its reactant and product concentrations to reduce the disruption and restore dynamic equilibrium. I'm going to use a couple different terms interchangeably throughout this podcast. Perturbations may also be called stresses, disturbances, or disruptions that would occur to a system that is in dynamic equilibrium. Let's look at three main examples of perturbations. First, a concentration change. Any changes in concentration to either the reactants or the products will cause a shift in equilibrium in order to restore and compensate for the stress. Number two, a pressure change as a result of volume change will perturb a system in which you'll need to consider the moles of gaseous reactants and products. Number three, temperature changes will also stress a system in dynamic equilibrium, and that stress will cause a shift in either the left or the right, either the forward or reverse reactions. Let's look first at how concentration changes can perturb a system in chemical dynamic equilibrium. When a quantity of a reactant or product is added, the system will shift, and that shift will occur to remove the added chemical. Let's look at this graphically, in which we have our reactants A and B combining to yield a product AB. In this animation, we have added reactant to the equilibrium system. We're going to add A. When A, so we're adding more of the reactant, it's going to push to the right, all right, to restore dynamic equilibrium. Here is the influx of A, leading to an overall increase of AB as the system favors the products, as the system favors the forward reaction. Now note a decrease in B. This decrease in B makes sense if you consider it for a moment. As A is added, that stress leads to a shift right to form more products. Well, if you're forming more products, that's going to require the consumption of B. So we see a decrease in B. Now, what do we see at the end? We see here that equilibrium has been restored, where the concentrations of the reactants and the products remain constant. That is defined as dynamic equilibrium. Now let's look at another situation here in which we're removing reactants. Let's remove B. When B is removed, there is a shift, and this time the shift is favoring the reverse reaction because it's trying to restore equilibrium. So if B is removed, the way to get more of that particular species is for A and B to push to the left in the reverse reaction and favor formation or restoration of the reactants. All right, so it's really cool. And if we look at this graphically one more time, B is removed, A increases. Why does A increase? Well, the shift is overall AB forming more A and B. So if B is removed from the system, that stress yields or leads to an increase in A, a decrease in AB, until we have restored dynamic equilibrium, at which point here we see graphically that the concentrations are remaining constant. Let's now consider changes in pressure. Let's look at a chemical system that we studied in the first video, in which 2 moles of nitrogen dioxide yield 1 mole of dinitrogen tetroxide. Let's first count the moles on the left of gaseous reactant. there are 2 moles, as indicated by the molar ratio. For every 2 moles of this reactant, we will yield 1 mole of the product in the forward reaction. So this is critical because when you are trying to assess how a perturbation will affect a chemical system, specifically dealing with pressure changes, you must count the moles of the gases on both sides before you can understand how the system will respond to that stress. So we have 2 moles on the left, 1 mole on the right. Let's now look at an animation to help understand this phenomenon. So here we have moles of A plus moles of B yield a product. The product is AB and is denoted as 2 black molecules as the reactants. So A is blue, B is red. Product in the forward reaction is AB, shown in black. So here we have a decreased pressure. As the system is perturbed, as volume decreases, pressure goes up. Well, how will the system respond? It's going to favor the direction with the least moles of gas. If pressure goes up because volume goes down, the system will, in this case, favor the forward reaction. Why the forward? Because it's the one with the least amount of moles. Let's look. On the left side of the equation for the animation, there's 1 mole of A and 1 mole of B, and they are gaseous. That's 2 moles. On the right side, there's 1 mole of gaseous product. 2 moles on one side, 1 mole on the other, just like our example with nitrogen dioxide and dinitrogen tetroxide. Same thing. So this shift, if we were to go ahead and get it into your notebooks, the equilibria will respond by shifting to relieve added pressure and to replace some of the lost pressure. So this is really kind of tricky to get a hang of, but in the end, you're just counting and looking at how many moles of gas are on one side versus the other. If there's an increase in pressure, the reaction will shift to the whichever side has the least number of moles. And hopefully that provides a bit of intuition for how this particular form of stress will lead to a shift in equilibrium. Lastly, let's look at temperature changes. For temperature changes, let's continue to look at this reaction, except this time I have shown you the reaction represented thermochemically. In other words, I have shown energy as part of the chemical equation. As you can see, the energy is shown as a product, which means it is produced or evolved, which means this is an exothermic reaction. In order to understand how stresses involving temperature change will respond and how they will affect a chemical system, you must write it thermochemically. It will help you out, trust me. So now that I have it written as one of the species, it's a product, I can begin to understand. Now, before you understand this video here, I need to give you a bit of background. Nitrogen dioxide gas is a brown, reddish, noxious gas. Okay? Dinitrogen tetroxide is a clear gas. So we have a color change that will allow us to see how the chemical system responds to a disturbance. So I want you to look at the equation real quick, and then we're going to make sense out of the video. For every 2 moles, again, of this reddish gas, it will yield 1 mole of the dinitrogen tetroxide, along with 58 kilojoules of energy released from the chemical system. Okay, so if we add heat to here, the system is going to favor the reverse reaction and push back to the left. Back to the left is producing a brown-red gas, nitrogen dioxide. So we can see this occurring. Now, let's look at the video. Here, the test tube is going to be placed into hot water. Look for the change in color. Look for it to become more red. There it is. As a result of added heat, the system pushed left to restore equilibrium. Please take a moment here and look at it again. Heat is added, system pushes to the left. Reverse reaction favored, and we see more of the red nitrogen dioxide as a result of the perturbation. Now you might say, how come it still has color when it's in cold? Recall that a system in dynamic equilibrium has constant concentrations of both reactants and products. So even though when it is placed in the cold water, we see it change and become not as red/brown, there's still nitrogen dioxide present. That's the definition of dynamic equilibrium. So when heat is added, this system will push left. Let's get some notes in your notebook real quick here before we move on. Increasing temperature of a system favors the endothermic reaction. In this case, it's pushing left, and the system will counteract the change by absorbing some of that extra heat, shifting to the left, favoring the reverse reaction. This is so cool, and if we have time, I'll conduct this demonstration for you in class. Now let's do one practice problem. Our system in dynamic equilibrium is one in which we have hydrogen gas reacting with iodine gas to yield hydrogen iodide gas. We're given the enthalpy value as positive 26.5 kilojoules per mole. That means that this is an endothermic reaction. Part 1. Hydrogen gas is added to the system. In other words, we're increasing the concentration of one of the chemical species. And the question is, how will this reaction respond to the stress of added hydrogen gas? It's going to push to the right. It's going to now favor the forward reaction, and we're going to see the concentration of the products, the hydrogen iodide gas, increase as a result of this particular stress. This is Le Chatelier's principle. Let's look at another stress. The volume is decreased. If volume is decreased, pressure is increased. So our system is compressed, pressure goes up. How will the system respond? What did I teach you to do? Count the moles of gas on both sides. So let's start with the left side. 1 mole of hydrogen gas, 1 mole of iodine gas. Let's look at the right side. 2 moles of the hydrogen iodide gas. So there's 2 moles on this side, there's 2 moles on this side. An increase in pressure as a result of a decrease in volume will have no effect because the number of moles of gas are the constant. They're the same on both sides. Reaction is unaffected. Lastly, the temperature of the system is decreased. What did I tell you to do? Represent this reaction as a thermal-chemical equation. For an endothermic reaction, we do that by showing the change in enthalpy as a reactant. Now it becomes much easier to conceptualize the response. Temperature of the system is decreased. What's going to happen if the temperature is decreased? We're going to see a shift, and that shift will be to the left. If we remove, think of it as just any other reactant. If we remove it, the shift is to make more of it. So if we remove heat from the system, the shift is to restore that heat. Okay, so the reaction will shift left. It will favor the reverse and will make more reactants. So we're going to see an increase of hydrogen gas, an increase of iodine gas as a result of the decreased temperature, as a result of that stress to the system. So our Georgia Standards of Excellence require us to look at the effects of altering conditions to a chemical system. That is Le Chatelier's principle. I will see you guys in class.